Hey, welcome back. Today we're going to be talking through an FRQ for AP Physics C Mechanics. This is number 3 from set 2, and it's from 2023. It's a good FRQ to practice for rotation, energy, and calculus, so let's go ahead and get to it. So it says a wind turbine includes a 3-blade system that rotates about an axis through the end of each blade as shown in the figure. Each blade has a length L and mass M, with center of mass located at a distance of L over 3 from the axis of rotation as shown in figure 2. So check this out. There is an offset. There's an offset right here from the axis of rotation to the center of the mass of the object. What does that imply? Well, that implies we're going to be using the parallel axis theorem. Okay, so let's continue to read the problem. It says, derive an expression for the rotational inertia of the 3-blade system. Express your answer in terms of M, L, and physical constants. The rotational inertia of each blade about an axis through its center is given by this equation right here. Let's say the rotational inertia of each blade is equal to the rotational inertia for the center of mass of each blade plus the I offsets. There is some value that this is offset by, and that changes things. So we could say the I for each blade. This offset is typically written as mr squared. That's usually how we write this out, where r is this distance that the offset value is by. But what we know is that this r value, we need to translate that into L, and they tell us what the offset is. In other words, we would say plus m, and then this would be L over 3 squared. Okay, so for the I for each blade, and we can sum these together and say this ends up being 3/18 ml squared. So that's the rotational inertia for each blade for its center of mass, but also for the offset that's involved. The issue, though, that we can't forget is that we want to take that and multiply it by 3. So we could say I for the system is equal to 9/18 ml squared, because there are 3 blades. Well, what does that equal? Well, that simplifies to 1/2 ml squared. So that's how you would do this problem right here. We may need this information further for further parts of the problem, as we typically do in problems like this. So in any case, let's take a look at B and see what it says. Okay, and so taking a look at B, it says when the wind blows, the 3-blade system operates at a constant angular speed of this omega right here, 2.6 radians a second. The length of one blade is given. The numerical value of the rotational energy of the system is that. So they've solved for that total rotational inertia that we had just talked about. Calculate the time it takes the outer edge of a single blade to complete 1 revolution. Okay, well, there's a couple ways of thinking about this. One way to think about this is just sort of the rotational version of average velocity. Let me explain really quickly. You don't have this equation on your equation sheet, but you probably have it memorized. You could say the rotational version of this, so you could say omega average is just delta theta, the change in the angle in terms of radians over delta t. That's a true statement. We know what the delta theta is right here. We don't know what the time would be, and we're going to assume 1 revolution. So assuming 1 revolution, we could put 2 pi radians in here and be able to get our answer. So we would isolate for t first, and you'd end up with 2.4 seconds. That's how I would think of it initially to begin with. But there's another way to do this as well, because when it talks about the time for 1 revolution, what is that? What is that as a concept? Well, as a concept, that is period. We are looking for period. And a very basic equation that we have on your equation sheet that's crucial dealing with period is going to be this. So you could just say t is equal to 2 pi over 2.6 radians per second. This is going to give us the same answer of the time for 1 complete cycle is equal to 2.4 seconds. Either way is going to get you the correct answer. So that's how you would approach B. Let's take a look at C. Okay, and so C says when the wind stops blowing, the angular speed of the system decreases. The angular speed omega of the system while slowing down is given as a function of time by the equation, where beta naught is constant with appropriate units as shown in the graph here. calculate the amount of energy dissipated from time equals 0 when the wind stops blowing until the system comes to rest. So when it says comes to rest, that's pretty important. If you think about this, this is asking about energy, and it's asking about how much energy it lost. So initially, it's useful to think of this as like a change in kinetic energy. That's not exactly what they're asking, but it's useful to think about this. The final energy minus the initial energy, right? Like that's one way to think about this. But they're not even asking that because the final energy is 0. They're just asking about this. What is this in a positive sense? So what's that rotating kinetic energy that we have for the system? Well, it turns out that we do have an equation for that. So it's 1/2 I omega squared, right? They've told us what the I value is previously. So that's this value times the 2.6 radians per second squared. And if you do the math, you end up with minus 2.3 times 10 to the negative 7 joules. Now, it's a little unclear from the problem whether we are supposed to write this as a positive or a negative answer. This is the amount of energy lost. But it turns out in the grading sheets, in the grading points, they note that you could write this as a positive or a negative answer to get the answer. Okay, let's move on to C2. It says derive an expression for the net torque exerted on the system as a function of t. Let me zoom out so we can read that. As a function of t as the system slows down. Express your answers in terms of these values right here. Okay, so what do we know? Well, we know that torque is equal to I times alpha. We now know what I is. We know what the I for the system is. But alpha, let's think about what that is. So remember, we have angular velocity. To get this, we're going to have to take the derivative to be able to get that, right? So you could say torque is equal to I times, and then this is going to be like d omega over dt. So torque is equal to I times, torque is equal to this business here. And looking back to see if we can leave I as is, we can. I just want to clarify, they're using I sub cis, so I'm going to go ahead and write that in. I might rewrite it to make it more legible. Should have left myself a little more room, but that's all you need to do for this problem right here. And we'll label this as CII. Okay, now part 3. Okay, now part 3 is a little bit tougher. It says derive an expression for the angular displacement of the system, delta theta, as a function of time. Express your answer in terms of those values and physical constants. Okay, so just as we had said before, we had to take the derivative of omega to get the alpha. We have to do the reverse. We have to do the integral of this angular velocity equation to be able to get the angular displacements. I mean, you could justify it too. You could say omega is equal to delta theta over delta time, right? And if you separate your variables, you could say, and if we just switch the order and take the integral of both sides, you end up with the integral of delta theta is equal to the integral of angular velocity dt. And so this ends up being delta theta is equal to the integral of omega dt. That's a proof of the idea that we're talking about. If we just take the integral of the angular velocity with respect to time, then we're going to get our angular displacements. So fair enough, we can think about how to do this. So we're going to say angular displacement is equal to the integral. Now we know what this equation is because we have it right up here. Okay, and let's think about what our bounds are going to be. This is going to be from time 0 to time t. Okay, the omega naught is just a constant, and this is going to be evaluated from t equals 0 to t equals t. Oh, I can't forget the negative sign down below here. And the subtraction that you would get from the lower bound being subtracted from the upper bound is counteracted by the negative that's already inherent in the function. So we get this turning into a positive value here. Now we need to be careful here. This e to the minus b naught times t. What is t? Well, t is 0. Okay, so let's think about that in just a moment. Okay, this is beta naught. when you have anything to the 0 power, it just is 1. So this whole thing is equal to 1, you could say, right? So I'm running out of room, but I'm just going to drag this down so we can work with this a little bit more. We would say delta theta is equal to, and let's look at what we have. We can clean this up a little bit, and sometimes it is helpful if we do. This is the kind of thing that you can do at the end of your FRQ if you have a little more time. You might get 1 extra point for cleaning some stuff up, you might not. So this is not a high value action here for the amount of time, unless you're a calculus whiz and you can do this stuff in your sleep, which it's really not that hard, but I'm just saying sometimes there are easier points to get than getting a bunch of lines of calculus to be able to understand the answer here. I do need to make that positive out in front because this was a positive term and that gets shifted over to the front. That's what we have here. And this becomes the second term over here, and that's the negative one. So just to clarify there, that's what we're going to have for our answer here, and let's move on to D. Okay, and so part D says the 3-blade system is now replaced with a second 3-blade system identical to the first, except that the second 3-blade system slows down according to the equation given. So this was our original equation right here. I wrote it in for comparison. It's the same, but what is different here, so they tell us our initial angular velocity is going to be the same. They do tell us though that beta is greater than beta naught, so that's important here. I want you to think about what that would do for this process. What it would do is cause omega to drop more quickly, so it approached 0 more quickly than it did previously in the previous version of the graph. This changes more quickly in a more negative sense. This is where it's not actually that easy to do, and I'm not that great at drawing on a tablet these curved lines, but you kind of get the idea. It's going to look something more like this. It's going to be essentially the same style of curve. Oh, you know what? I should make this start at basically the same. I should curve this up a little bit more so it still starts at 2.6. But it's going to drop down faster and come down to eventually 0, or if we can pattern it somewhat like an asymptote like they have here, then that would be good as well. In any case, that's all you have to do for D, and I do want to say that I have done lessons on an entire year of physics as well as most of the ideas for AP Physics C Mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.